Hello everyone, welcome to this tutorial. In this video we will learn how to build and analyze the H-beam, H-steel beam in Abaqus step by step. And here in this video I will show you everything clearly from creating the parts to running the job and viewing the results. So let's get started and see how to model this steel member which we have in Abaqus in a simple and practical way. So here are the dimensions of the steel beams which we will be building in the Abaqus today. The total length of the beam is 19,000 millimeter, which is 19 meter, and then we have the width of the web is 300 millimeter and the total height of the beam is 900 millimeter with the flange thickness of 28 millimeter and web thickness of 16 millimeter. Alright, so here we have the interface of the Abaqus. Let me go ahead and start with creating a beam. So we will start with the part module. First we will go here to create part, and we are going to call it this as a beam, and we are going to model this beam as a 3D model, and the type of model we will be using is the deformable. And in the base feature we will be using the shell element which we usually use for the beams in Abaqus, and the type we will be using as a extrusion. So the approximate grid size Abaqus is giving us is 200. We are going to make it 900 as the overall height of the beam is 900. So this is an approximate size of the grid. So we press continue. So here is the grid, and these are the tools which we will be using to build the cross section of the beam. Okay, so before creating the geometry of the shell beam we have, I wanted to clarify one thing, that in order to make a shell part we are going to make the geometry in the part section as the center cross section line of the beam. Okay, here we are. We have created the geometry of the cross section of our shell beam with the top flange width of 300 millimeter, and the height now is 872 because we have created the center line of our beam. And when you press done, here is this option of the overall length. So the overall length of extrusion we have for our beam was 19,000 millimeter, and then if you press OK, so here as you can see it is our 3D model of our beam. Okay, so after creating the part we are going to go to the property module, go to create a material, and then I can call it 355 material, and then we are going to go to add the mechanical properties and add the elastic properties, and the Young's modulus we have was 205000, and the Poisson ratio we have is 0.3. so here you can see in the material manager we have created the material property for the steel beam we already have. Okay, so after defining the properties for S355 steel we are going to create sections. So in section I'm going to create two sections for flange and web because the thickness of flange and web is different. So I am going to call it section 1 flange, and then I'm going to click on the shell element and then click on homogeneous, continue. So we have these options, the shell thickness. So the thickness of our flange was 28 millimeter, and then the properties we already selected as S355 material, and the thickness of integration point across the thickness is 5, so we are going to keep it as it is. Press OK, and then we are going to create another section 2 for the web. Again, shell element, homogeneous, click on this one. The thickness of our web was 16 millimeter. I'm gonna keep it 16. The material is same. That's okay. So as you can see, we have the created for the flange and for the web. Okay, so after this we are going to assign these material sections to our beam. So we are going to go to assign section, and then we can click on the web, done, and here you can see we have created a section 2 for the web, and then press OK. So as you can see, it turns green, and similarly we will do this for the flange. So we select both top and bottom flange, done, and then we select the flange, and then OK. So as you can see, the color changed. That it means that the material property has been assigned. But now, as you can see here, we cannot see the thicknesses of our flange and web, and so in order to check those, we can go to the view, and then we can go to the part display option, and here you can check the render shell thickness, and the scale factor is 1. Apply. Okay, you can see the thicknesses of both the flange and the web is now visible in our model. Okay, so after the properties has been assigned, we can go to the assembly module. Okay, so now here the interface doesn't show anything. We can import the parts we already created by clicking here, and then you can see we have only one part, which is beam, so we can import that beam here and then press OK. Alright, so now as you can see, we have our beam, and now in our assembly module you can translate it or position it when you have different parts together by using the translate, and then the rotational patterns we already have, and you can resize as well. So sorry, the rotation of the instances. So these are the buttons you can use when you have different parts connecting together. Alright, so after setting the assembly, we are going to go to the step module. Here we will be creating a step 1. So you can click on the create step, okay, and then you can name it whatever you want to name it, like loading step. So as we will be doing only the deflection analysis, so for that we are going to use the general static one. If you want to do the dynamic analysis, you can use the dynamic implicit and explicit, but that depends on the analysis you want to do. So for now I'm going to select the static general. Okay, and here you can give the description, the explanation about the step you want to do, or you can keep it empty, and the time period we are going to keep it 1 second, and then the non-linear geometry, so we will consider the non-linear geometry in our model, so I'm gonna make it on, and then we go to the incrementation. So yeah, so we need the analysis to be done in different steps, not in 1 second. So I'm going to give the initial increment size as 0.01, and then the maximum step we can go from maybe 0.1 is good, and then the maximum number of incrementation we are going to increase it a little bit, because sometimes the Abaqus use different number of steps to analyze some parts, so that's why we are going to give them a large number of increments. and the others you can keep it as it is. Okay, so now we press OK, and you can see the step we created in the step manager. Here is our loading step with the non-linear geometry on and the time step of 1 second. Okay, so after creating a step, we can check the field output. You can click on the manager, and by default one output is created if you click on edit. So here in this menu you can see that there is a list of parameters you want to study, or you want to analyze, or you want to get a result after the analysis is done. For example, stresses, strains, displacements, force reactions, contact. So you can uncheck those which is not required, or you can check those which is required in your analysis, like thermal, electrical and magnetic. We don't need those, so for now we are going to keep it as it is, the default parameter selected by the Abaqus. Of course we will be needing the stresses, strain and the displacement, so it's already checked in, and then press OK. And similarly in the history output as well, so it's already been created and we are going to keep it as a default. Okay, so after the step module has been completed, now we are going to go to the interaction module, but we have only one part instance, so we don't have any different or 2 or 3 paths connected together, so we don't need to add any interaction here. So now we are going to go to the load module. So first we are going to apply the load. So in order to apply the load, first let me show you what kind of load we will be applying on. Okay, so in this example we have the uniformly distributed load of 45.6 kilonewton per meter, and we are now going to convert this load into an equivalent surface pressure on the top flange for the 3D shell model. So how we are going to apply this load in Abaqus? We go to the create load, okay, and we will apply this load in the loading step, mechanical, and then we select the pressure load. Okay, so now Abaqus is asking me about the surface on which we applied this pressure load, so I'm going to select the top flange. As you can see, the whole top flange surface is selected. Done. So now Abaqus is asking me the side of the shell. I'm going to select the purple load. Okay, and we are going to keep the distribution uniform, and the magnitude we calculated was 0.152. Press OK. So as you can see, the uniformly distributed load is applied. Now we know that this beam is simply supported. One side is pin and one side is roller support, so we are going to apply those here in the boundary condition. So we are going to change this into the initial step, mechanical displacement and rotation. Okay, so I'm going to fix one side with the pin support, and for the pin support we have restricted the displacement in X and Y direction. Okay, and then for the second roller support we are going to constrain the displacement in Y direction U2 only. So we are going to change this. Okay, and similarly we are going to create boundary condition initial. Okay, and then we will select this region, and then press done. So we are going to constrain only the vertical Y direction displacement. Okay, so this is roller and pin support we have. So as you can see, we have the loads Apply uniformly distribute load and pin and roller support beam. Okay, so after our load module is completed, now we are going to go to the mesh module, and here we are going to apply the mesh, and we are going to select the part. Okay, and then we are going to select the seed, the global seed, and then there is a approximate global size of the meshing. So Abaqus is giving me now the global size of the mesh is 30. We can keep it as it is, and we can change it depending on the model and the specification of your analysis. So for now I'm going to keep it as a default and then apply. Okay, and then here I am going to select the element type of the mesh. Okay, select the old beam, a standard, linear and reduce, and here you can see the shell. Alright, it's already been selected, done, and if you click on this one, mesh the part. Okay, so here as you can see we have done the meshing of our beam as well. It looks good. Okay, so after meshing is done, we are going to go to the job module, and we are going to select the create job. I'm going to name it a job 1, let's say static analysis, and then press continue. Okay, so in the job manager now here you can see job 1, static analysis, and now the only thing you will do is to submit the job, and then press submit, and as you can see it is submitted now, and when it's complete then we'll be back for the results. Okay, here we are in the visualization module after completing the job. So we can now see the deformed shape of our beam. Here as you can see the displacement, and from here you can see different stresses and everything of your required analysis. So I think that is all that we have for today. I'll see you in the next tutorial. Thank you so much.